Welcome to our first video of this week, in which we continue our discussion of Markov chains. In particular, we will discuss how a Markov chain behaves if we run it for a long time. It means the asymptotic behavior if the running time tends to infinity. We already had a look at the mean recurrence time, so it answers the question how long it takes on average to return to a state I. So based on the time of first passage, tau I, we have the mean recurrence time mu I, meaning if this Markov chain is currently at state I, how often will it return to the state? Mu I is defined as the expectation of the first passage time to state I, given that we start the Markov chain in state I. We have already learned that the mean recurrence time for transient state is infinite, because it might be possible that the chain does not return, in which case we have to wait for a recurrence infinitely long, and that of course makes the mean recurrence time infinite. On the other hand, for recurrence time, the mean recurrence time might be finite, but it also might be infinite. So based on that observation, we already defined or made the distinction between null recurrent states and positive recurrent states. And that also leads us now to the asymptotic distribution. So we are interested in the proportion of times that the chain will stay in a certain state if we have already run it for a long time. And because the mean recurrence time is mu I, means that on average only every mu I steps the chain will return to the state. The proportion of times that the Markov chain is in that state should be 1 over this mean recurrence time. And that leads us to the following result, based on our observation on mean recurrence times, that if we start the chain in state I, then the probability that after a long number of steps, that the chain will be in state J. So we let tend n to infinity, look at the transition from state I to state J. Then this should be 1 over mu J if I and J are in the same class, so they communicate with each other. And J itself is a recurrent aperiodic state, which means that actually, of course, in the long run, it will be still relevant. Now, of course, if we start the chain in a different state, so in a state that is not in the same class as J, then it might actually happen that the chain never goes to the state class of state J, sorry, in which case it then of course will not visit the state J, and therefore this probability of transition to state J must be multiplied by the probability of ever making a transition from I to J. And once the chain is in state J, then of course it will again and again return with an average time of returning to being mu J. So here, compared to the first case, we have an additional factor Fij. An important observation in the first cases, so we start the chain in the same recurrent class as state J, then the probability for a transition from I to J does not depend on the starting state in the long run. So it only depends on state J. So firstly, again, our definition of positive recurrence and null recurrence, now expressed in these transition probabilities. We call it positive recurrent is namely this 1 over mean recurrence time is positive, and it is null recurrent if 1 over mean recurrence time equals 0. So that means that the probability to meet the chain in state I is actually 0, even so, of course, from again and again, because it's a recurrent state, the chain will be in that state. But in this situation, there are infinitely many alternatives, and the distribution is too much spread out to have any positive probability mass in any of these states. One can simply show that together with recurrence and transience, these notions of positive recurrence and null recurrence are also class properties. And therefore, again, we can restrict our attention to one member of the class and prove recurrence of a positive recurrence, null recurrence for one element only, if that is possible. So let us summarize the consequences of our findings. So firstly, within classes, the asymptotic behavior of a Markov chain does not depend on the starting value. So we have a distribution in the long run that has completely forgotten where the chain started. For positive recurrent classes, we really get a proper distribution. So these probabilities to be in a certain state are strictly positive for all possible, for all members in the class, because every member in the class is positive recurrent and therefore must have a positive limiting distribution. On the other hand, for transient or null recurrent classes, the probability to stay in a particular state decreases to 0. For transient states, this is clear because after finitely many times, these states are no longer visited and therefore in the long run, of course, have a probability of 0. For null recurrent, even so these classes and the states in the classes are visited again, the probability distribution still decreases to 0, just because it's not a proper distribution. The distribution is too much spread out over the infinitely many alternatives. Now, if we have a recurrent class, we already know such a class cannot be left and therefore is closed. And because of that, a null recurrent class must have infinitely many members, because otherwise we would have a contradiction that after that we basically have a distribution, so a probability 1 to stay in the state, but a probability 0 to be in any single state. That is not possible. So therefore, like for closed transient states or classes, null recurrent classes must also be infinite. So finally, it is clear that if we have more than one positive recurrent class, then of course the limiting distribution depends on the starting value. Just we might start either in the one class or the other class, then of course the chain can never visit the other class, and therefore the distribution is either completely concentrated on the one class or on the other class. And if we start outside the class, it depends on the probability to get to either the one class or the other class. So we get a mixture of the two limiting distributions that solely concentrate on one class each. Now, having said that, we get to the very important notion of a limiting distribution. So we say that a Markov chain has a limiting distribution if these transition probabilities for starting in state I getting to state J after infinitely many states, transitions, this limit being denoted Pj is the limiting distribution. If this exists for all possible states I and j, and of course is a proper distribution, so the sum of the pi equals 1. Very important, we say only that the Markov chain has a limiting distribution if such a distribution does not depend on the starting state. So that means, for instance, if we have Markov chain with two recurrent classes, it cannot have a limiting distribution. It's simply that any distribution that we get in the limit would depend on the starting state and therefore cannot be the limiting distribution of the Markov chain. So this leads us to the following result. If xn is a Markov chain, then it has a limiting distribution if and only it has exactly one aperiodic positive recurrent class C, such that the probability of making eventually a transition into this class, so J being here in the class and I being any starting state, possible starting state of the Markov chain, that these probabilities for eventually going from I to J are 1. That, for instance, rules out that we have one positive recurrent aperiodic class and another transient class with infinitely many elements that is also closed. Note that could be possible, but that would be ruled out because from that transient class we cannot go back because it's closed, we cannot go back to the other positive recurrent class. So situations like this would be ruled out. From any state outside the positive recurrent aperiodic class, the Markov chain eventually goes to this one aperiodic positive recurrent class of this probability 1. Only then we will have a limiting distribution. And as the important characterization of the limiting distribution, so provided our assumptions here hold, then the limiting distribution must satisfy this equation here, which we can also write in matrix form if this is the vector of probabilities for the limiting distribution, and this is a transition matrix, then multiplication of this vector P by the transition matrix gives us back the vector of probabilities P. The idea is that if we have run the chain infinitely long and the chain therefore is in distribution P, then applying yet another transition will not change the limiting distribution, because one transition more after infinitely many transitions does not make a difference. So that intuitively gives us this equation system, either pointwise or as in vector form described. Now this equation system in itself also has a different interpretation. So again, we have in vector form P times transition matrix equals P. And without having to wait to run the chain infinitely long, we can actually say, okay, if the chain is in currently has a distribution P, so we have a certain distribution for the Markov chain being in the different states. And if that is P, and then the Markov chain is applied for one time, then again we have the same distribution. So the distribution does not change after applying one transition of the Markov chain. So the distribution is invariant under the transitions of the Markov chain. We call distribution of this kind an invariant distribution or a stationary distribution. And in that case, you would have a stationary Markov chain where the distribution for the Markov chain to be in the different states does not change over time. So this equation system here describes naturally a stationary or invariant distribution. And we find that the limiting distribution by the previous result. So here we found that for the limiting distribution, if we have one, then it satisfies this equation system, and therefore is the limiting distribution of a Markov chain also the stationary distribution. Now the question arises, okay, we have two notions now, the stationary distribution, where we assume, okay, we start the Markov chain in that distribution, then the Markov chain over time does not change the distribution to be in this different states. And we have the notion of a limiting distribution that we get regardless of starting state in the long run. And the question is, are these the same? They are described by the same equation system, or at least they satisfy. And we already see that a limiting distribution is always a stationary distribution. So is a stationary distribution also always the limiting distribution? So that raises the question, when do we have a stationary distribution, and do we actually, are the conditions differ from the conditions for the existence of a limiting distribution? So suppose Xn is a Markov chain, then this Markov chain has a unique stationary distribution P, if and only if it has exactly one positive recurrent class. We're not saying anything about the other classes, as the stationary distribution will anyway concentrate on the one positive recurrent class. What we rule out is, firstly, that we have more than one positive recurrent class, but we could have null recurrent and transient classes. Secondly, what we do not rule out is a periodicity or periodicity. So, because that is the difference. So here we only say the chain has exactly one positive recurrent class, and the stationary distribution then will concentrate on this class. We can have other classes that are transient or null recurrence. The stationary distribution will simply be 0 on those classes. We can have other states from which we might not reach the exactly the one positive recurrent class, with probability 1 does not matter if we start the Markov chain inside or according to the stationary distribution inside the positive recurrent class. All other states are anyway of no importance. So that is a big difference. Stationary distribution can exist under much broader conditions because the stationary distribution anyway will only pick the one class of interest, namely the positive recurrent class. So as I already noted, one word that is missing in this theorem is the aperiodicity. As it is simply not required, we can have periodic Markov chains and still stationary distributions. And as a simple example, look at the Markov chain that has this transition. So that is our simplest example of non-trivial Markov chain, which is described by visit always the other state. So we have two states, and each transition, the Markov chain goes to the other state. If we start this chain here with the stationary distribution of a half and a half, then it's clear that after any transition, we still have probability a half to have the Markov chain in each state. So the distribution is not changed, and therefore this is the stationary distribution. As I already said, the stationary distribution concentrates only on the positive recurrent class. All other classes are irrelevant for the stationary distribution, and therefore we can have many of these other possibilities as long as they are not positive recurrent. If you have two positive recurrent class, of course, we can have a stationary distribution on one and on the other, and any mixture of those. So the uniqueness then would be violated. So that means that this is really a necessary condition, that we have exactly one positive recurrent class. As an example, suppose that we have two urns with 3 balls in each urn. So in total we have 6 balls, and 3 are white and 3 are black. They're somehow distributed in the 2 urns. And then we create a Markov chain by at each step taking 2 balls, 1 from each urn each. And then, so these balls are drawn randomly and then exchanged. So we always take 1 ball from each urn and put each ball into the other urn. Then to describe the system, we have in total 6 balls, 3 white, 3 black. If we know the number of, say, white balls in the first urn, then we have described the system completely. We know the black balls in this urn, and therefore we also know the white and the black balls in the other urn. So xn denoting the number of white balls in, say, the first urn after the nth step is a complete description of this Markov chain. Then we have the following transition matrix. So if we have 0 white balls, then definitely in the other there are 3 white balls. 1 of them will be taken and put into the first urn. So we have a transition with probability 1 to state 1. On the other hand, if the state, and the same here is for having 3 white balls, then of course we will have in the next step definitely 2 white balls. And the other transition can be described similarly. We have, so if the chain is, so we have currently 1 ball, then we need the probability that this one will be picked and put into the other box, while in the other box, the white ball is not picked, and therefore black ball comes into the first one. So this then would lead to the transition from state 1 to 0. That is the probability. While here we have several possibilities to stay in the state, and same for this state here. So one can calculate all these numbers of this transition matrix. And it's clear by these transitions that the chain is irreducible and aperiodic. We can also make the graph. So we have 0, definitely movement upwards. One, 2, and 3. These are transitions with probability 1, and the others according to this scheme. Obviously, this chain is irreducible, one class, and aperiodic. As I actually forgot 2 arcs, namely those self loops that we only have in states 1 and 2, and because of them we have a periodicity. In this example, to find the stationary distribution, which in that case is also the limiting distribution because we have only one irreducible finite positive recurrent class, we have to solve the equation system P equals P times P. So we have to multiply the transition matrix from the left by the vector of the probabilities of the stationary distribution. So if we do that for the first line, so recall this is our transition matrix. So we multiply this first line by the vector of probabilities. So we get that P1 equals a 9th P2, and for all other probabilities P2 to P4, we get similar equations. And additionally, of course, this needs to be a vector of probability, so a probability distribution, so the probabilities need to add up to 1. So we have 5 equations with 4 unknowns. Because of the symmetry of the problem, we can easily see that P4 equals P1 and P3 equals P2. We simply have to change the interpretation of white and black balls and this system is completely symmetric with respect to white and black balls. So that gives us these 2 equations, and we only have 2 unknowns left, P1 and P2. And of course, using here this equation system, we can express P2 in terms of P1, namely it's 9P1. And then as P1 to P4 need to add up to 1, we find that P must be equal to 1 over 20, 9 over 20, 9 over 20, and 1 over 20. So here we have the factor 9 between P1 and P2, and in total, and P3 equals P2, P4 equals P1, and in total they add up to 1. So that gives the value in the denominator to be 20, namely the sum of these 1, 9, 9, and 1. Now, at the end of the last lecture, I introduced the notion of ergodicity, and the definition said a Markov chain is called ergodic if it is irreducible and positive recurrent. Rather than being a definition of ergodicity, this is really a theorem, namely that if a Markov chain is irreducible and positive recurrent, then actually it has the property of ergodicity, which usually outside Markov chains is in generally described by having certain mean properties. Namely, we have ergodic theorem that if we run the Markov chain and we have observation xt, and we take the average over time of these observations xt, say a function evaluated of these values, then this average over time will converge, almost surely, will converge over to an average of the same function on the states with the probabilities of the stationary distribution. So this is an average over the states where the states are weighted by the stationary distribution or to the limiting distribution of the Markov chain. And whenever we have such a property, we have an ergodic chain or ergodic process. And for a Markov chain, we have this property if we have an irreducible and positive recurrent Markov chain. Now, one problem that we have is to find in more complex situation whether a class or a state is transient or positive recurrent, or of course null recurrent. We have in the literature the following interesting theorem that gives us a complete description. So if you have an irreducible aperiodic Markov chain, so we have one class of interest. The question is this class transient or null recurrent or positive recurrent? Then if P is the transition matrix, we let BQ be the transition matrix with the first row and column, so everything that has state 0 in there being deleted. Then we find the following characterization. The chain is transient if and only if the equation system Q times Q equals Q has a bounded non-zero solution. Of course, a zero solution is always possible, but the question is, do we have a non-zero solution and is that solution unbounded? So we have all these values Q that solve the system are they smaller than some value K, where K is a fixed finite value. Then the chain is positive recurrent if and only if the equation system P times transition matrix equals P has a strictly positive summable solution. That is exactly our system that defines the stationary distribution, or also the limiting distribution in this case, because we have the irreducible aperiodic Markov chain. And that is exactly what we already know. This irreducible aperiodic chain has a positive recurrent, or in the case where this class is positive recurrent, we have a limiting distribution and vice versa. And the limiting distribution or stationary distribution is exactly defined by this equation system. Very important, the solution must be a proper distribution. So any solution must be strictly, firstly, of course, positive. So we don't have anywhere zeros. And also it must be summable so that it can be converted into a proper distribution. Then what is left if you have a null recurrent, if the chain is null recurrent, then this equation system has still a strictly positive solution, but it's no longer summable. Anyway, we don't have to solve this situation separately, because we already know if we check for transients and positive recurrence, we already know if both are not satisfied, then the chain must be null recurrent. There are no other possibilities than those three cases, and therefore this is actually the leftover if the two other cases are invalidated. As an example, to fill this with life, we look at the reflected random walk. So that was our example from the last tutorial, where we have a drunken person moving upwards towards home with probability P, going backward to the pub, which is at state 0, with probability Q, and having another beer with probability Q. So formally, our transition probabilities are described by this system here. And a Markov chain like this is also called theoretically the reflected random walk, as we have a random walk, not necessarily symmetric, for P non-equal to a half. This is an asymmetric random walk, but at 0, rather than going beyond 0, the chain is reflected backward upwards. Of course, looking at the picture, we have an irreducible aperiodic Markov chain. And we will prove the following results, namely, if P is larger than Q, this chain is transient. If P equals Q equals a half, it is null recurrent. And if P is smaller than Q, it is positive recurrent. For the proof of the transients, we have to look at the equation system. So we have here our transition matrix. We multiplied from the right by a vector, here x1 to x infinity. And as we leave off state 0, we only have here the sum from 1 to infinity, and we have here elements xi from state 1 upwards. And we have to show that this equation system has a bounded non-zero solution. And if we look at the first line, so for x equals 1, that is exactly P times x2, and therefore so firstly, looking this way, we have always at a state that it either comes upwards from state 1 below or moving downward from a state above. And so we have the system, so xn equals pxn plus 1 plus q xn minus 1. Actually, it's an example of what we will later on call the first step analysis. If we start in a state, then after one step, we are either upward or downward in states 3 or 1. Or if we are in state k, then we are in state k plus 1 with probability p, and in state k minus 1 with probability q. And that is what we have here. And that equals xn according to the equation system. And xn can be written as p plus q equals 1 in this form. And then we can group the p's together and the q's together. So we have an xn plus 1 minus xn on the one side multiplied by p, and xn minus 1 on the other side multiplied by q. We divide by p and we get this recursive system, so that actually xn plus 1 minus xn equals theta, the increment is n one step downwards, and recursively we find that this equals theta n times x1, where in the final step x2 minus x1 by this first equation simply becomes q over p times x1 and not x1 minus x0, which does not exist in this case. Yeah, so that is the terminating condition here for this recursive system, and we can express everything here, each increment of the vector of x by this in this form, where theta equals q over p. Then our xn here can be written as x1 plus all these increments. So for I equals 2, we have here x2 minus x1, and the x1 cancels out. With the next one, it's everything cancels out, but xn here. So that is what we refer as a telescopic sum. So we take xn minus 0 and fill in the intermediate terms to write it in this form. Now, because of our findings here, we can write this as a sum from I equals 0 to n minus 1 theta to the I x1. x1 is common factor. So we actually have here a partial geometric series. And this sum here becomes 1 minus theta to the n divided by 1 minus theta, according to the analytic result for such a partial geometric series. Of course, only if p is non-equal to q. And if p equals q, this factor, of course, is 1, and we simply get here for this sum n times x1. Now, n times x1, certainly for n to infinity, is not bounded. And here, this here as well, is only bounded if, namely, theta to the n is bounded, which is only the case if q is smaller than p. So this factor here, q over p, is smaller than 1. That concludes that we have transients according to this criterion only if q is smaller than p, and the person has a higher probability of going upward towards home than going downwards to the pub. For the proof of positive recurrence, we have to look at the stationary solution. We have to solve this system. And like in the previous case, we find from the first multiplication, so for the system with P1, we find that P1 equals theta tilde times P0, where theta tilde now is P over Q. And by similar steps as in the proof of the transients, we have Pn equals, of course, P plus Q times Pn. And from this equation system, this equals P times Pn minus 1 plus Q times Pn plus 1. So here, P and Q actually are reversed or swapped compared to the proof of the transients. And therefore, we can similarly, as in the previous proof, find the following recursion system, that Pn plus 1 minus Pn now is expressed as multiples of P0 with this factor here. And again, arguing similarly as before, we have a non-zero solution if and only if the theta to the n is bounded. And as theta tilde now is p over q, we need to have p smaller than q, which is exactly what we stated. If p is smaller than q, we have positive recurrence. Now, finally, if the chain is not positive recurrence, p smaller than q, and not transient, p larger than q, then it must be null recurrence. So that is the case p equals q. So that finishes our discussion of stationary and limiting distributions. In the next part, we look at exit distributions and exit times. So about probabilities that something eventually will happen, or the mean time until something will eventually happen. As an example, look at the situation where we have a student taking exams to pass a course. As usual, there is an exam, first sit exam and then a resit. Then the student eventually might pass the course or simply might give up and drop out. We assume the following simple situation. So the student usually, of course, starts in the exam. So first takes an exam, then passes that with, say, probability 0.65, in which case, of course, he has passed the course and never has to redo anything, so stays in that state. Might immediately give up and drop out with a 5% chance. With a 20% chance, the student goes to the resit and takes that, passes that, or drops out, or if not passing, then takes another turn of the course and takes again the first sit exam. The student might also not go to the resit, but simply wait immediately for the next opportunity to take the course and take again the exam. So assuming that this is the situation, we might be interested in the following question. What is the probability that the student eventually passes the course? What is the probability that the student takes a resit, so ever visits the state? And how many times does the student take on average? So how many times does the student spend here in these two states before either dropping out or passing the course? It's clear that this Markov chain has one transient class here, namely those two exam situations, and two recurrent classes, namely 3 and 4. Both consist only of a single state and therefore are called absorbing. So a state is called absorbing if you have the probability starting in state I, staying in state I being 1. And here, of course, 3 and 4 have exactly these possibilities, transition probabilities of 1 to stay in this state, and are therefore called absorbing. Now, to solve this first problem in finding the probabilities to eventually passing the course, so the transition is the time of first passage to state 3 must be finite, and assume that we start in state I, call that the probability Pi. In particular, of course, we're interested in the probability P1. So starting with the exam, what is the probability of passing the course eventually? The important observation is that this probability here actually repeats itself once we are at a later time and the Markov chain is in a certain state. So the probability that eventually the student passes the course, given that at time t the student is in state I and tau 3 is larger than t, so the student not already has passed the course. This probability is the same as the probability pi from the beginning, so the probability that tau 3 is finite given that the student starts in state I. Okay, so after t steps, knowing that we are in I, we have the same probability because this is a probability that looks into the infinite future, something eventually happen, and there a few initial finite steps do not matter as long as the state in which we start is the same. And by that, we can actually have a look how the probabilities change if we do one step of the Markov chain. And because the probabilities are the same, they're related by the following equation system, namely P1 starting now, eventually passing the course is the same as doing a transition to state 1. So doing the exam, not passing it, and redoing it in the next year. And in that situation, then eventually passing the course, plus the probability for a transition from 1 to 2. So the student fails the exam and decides to take the resit. What is the probability then starting from doing the resit? The student will eventually pass the course, plus the probability of making a transition from 1 to 3, so passing the course, times P3. And here, of course, by the definition, we already find that P3 actually must be 1. In a situation that the student has passed the course, the probability of ever passing the course, of course, is 1. Likewise, these last parts are of no relevance because P4, the probability of ever passing the course, given that the student has decided to drop out, is 0. So using this, we can actually eliminate those two parts, have here constant, and then we have a equation system that we can solve for P1 and P2. This approach is called first step analysis because we look what happens after doing one step and relating the probabilities from before the step and after the step. And because of this observation that these probabilities we are interested in do not depend on the particular time, this gives a system that we can solve. As a more classical example, we look at the gambler's ruin problem. So for more financial interpretation, suppose that you have bought some stock for the price of K and want to sell it at the price of capital K. For simplicity, we assume that the stock price follows a random walk, so it can either move up by 1 with probability P or move downwards by 1 with probability 1 minus P. You sell as soon as the price reaches capital K. However, as soon as the price hits 0, your investment is no longer traded and you have lost your investment. So we are interested in the probability that we can sell at the price of K, so the Markov chain reaches state capital K before reaching state 0. We can describe the situation even so the underlying Markov chain of the stock is not bounded by the values 0 to k. Of course, by our financial interpretation, it will be bounded by 0. So it will always end up in the state 0 whenever it reaches it. But otherwise, it will not be bounded by k. But as we are selling our investment, we are not interested in the future after that. So we also treat k as an absorbing state. So we have here a big transient class that can either be left to the right to the absorbing state k, or to the left to the absorbing state 0. We are interested that the one in the probability that the one absorbing state is reached before the other. So let pk be the probability that our Markov chain takes the value capital K for some time n, given that we start in state small k. Here it is clear, as soon as the chain reaches 0, it cannot leave this state, and therefore we don't have to say anything like reaches capital K before 0, because that is included in our description here of this Markov chain. So again, we use first step analysis. So the probability of eventually reaching capital K starting from small k can be related to the probabilities one step later by looking at one transition. So that is pk plus 1. So we make a transition to state k plus 1 with probability p, and a transition to state k minus 1 with probability q. So that is the one-step transition. On the other hand, we can write pk as p plus q times pk, p plus q equals 1. And that is valid for all states 1 to k minus 1. And on the other hand, of course, we know that p0 equals 0 once the chain has reached state 0. There's no chance anymore to leave that absorbing state and ever reaching capital K. On the other hand, if the chain has reached capital K, we have sold our investment and we are also done. The Markov chain is also absorbed in state K and never can leave it again. So with that, we can proceed as in the problem with the transients. And that leads us to the following equations. So here again, we let theta be q over p, and we can express pk as this factor times p1 if p is not equal to a half, not equal to q, and it is k times p1 if p equals q. Then to find p1, we can solve this system for a situation where we know the answer. So we know, for instance, that pk must be 1. So if we plug that in, p capital K equals, for instance, here in this case, capital K times p1. And as p capital K equals 1, we find that p1 must be 1 over capital K. And we find, therefore, that pk equals k over capital K. On the other hand, in this situation, we find that p capital K is 1 minus theta to the capital K times over 1 minus theta times p1. So again, p capital K equals 1. So p1 equals 1 minus theta over 1 minus theta to the capital K. And that actually leads, plugging that back into these equations for general K, that the 1 minus theta cancels out and is replaced by a factor 1 minus theta to the K, capital K. So we have this general solution for the probabilities. So in particular, in the symmetric case here, the probability of ever reaching the upper state linearly depends on the starting point. It gets higher as closer the starting point gets to the upper bound. If we, for instance, let k be arbitrarily large, so we let tend it to infinity, then we have for the probability of ever reaching the upper state, so having the Markov chain tending to infinity, we have a probability of succeeding with being 1 minus theta to the k, where theta is q over p, and we need actually for this to be a proper distribution that q is smaller than p. So the probability of going upwards is larger than going downwards. Only then, of course, we can have a hope that the Markov chain eventually reaches the upper end. And otherwise, we have here a probability of 0. So the Markov chain eventually will end up in the absorbing state 0 if q is smaller or equal p. Q is larger or equal p. So this includes the case q equals p equals a half. But otherwise, if anyway the probability of going downwards is larger, the probability of ending up in the absorbing state equals 1. Finally, we look at the mean time spent in transient states, and by that also then the mean time spent in all transient states, and therefore needed to exit the transient states to first time visit one of the absorbing states. So for that, we look at the number of times the chain stays in a certain state. So we simply count the number of times the chain is in state J. And we know that the n-time transition matrix Pijn, so the probability to go from I to J in n steps, can be, by the Chapman-Kolmogorov, can be written or broken down into a one-step transition and a -1 transition. And with that, we can rewrite our expected mean time spent for state J, given that we start the Markov chain in state I, as the sum of the probabilities for a transition from I to J in n steps. So this would be the expectation of exactly this indicator function. So given that x0 at is I, and then xn equals j, the expectation for that is exactly the transition Pij for n steps. And we have here this infinite sum. And now we simply break that into the first step transition. So, well, firstly, we say we leave off the first step here, n equals 0 to infinity. For a zero step transition, of course, we only get a 1 if I equals j. So we have a delta ij taking the value 1 if and only if I equals j. And otherwise have the remaining parts from the sum. And now we apply exactly this equation, plug that in, and swap the integrals. So we have here the sum over all states, PIK, one-step transition, and have here now the sum for n equals 1 to infinity for the n-1 transitions. Now, these are now can be considered as exactly the probabilities for xn equals j, given that x1 equals k, making a small step as we have a time homogeneous Markov chain that then also equals the same expression with the time index one step down. So starting at time 0 at k, having here the sum of the indicator functions and the total sum being nj, we have the expectation of nj. So what we find, this is in principle again a first step analysis. We have this expectation, then we already have one time spent in the state I, if we start in state I, and otherwise we make a transition from state I to k, and then look at how many times are left, how many times the state will spend in state j, given that it is now in k. And now the observation is that this expectation is the same as the expectation that we started with due to time homogeneity and due to the fact that we look into an infinite future, and the one translation in the time step does not matter. So we have the same expectation, and now again we can solve the whole system. So writing this in terms of matrices, so if Mij is exactly the expected time spent in state j, given that the Markov chain starts in state I, we have here M equals identity matrix, that's the delta ij, plus transition matrix times the same matrix M, and we can solve the system for M. Yeah, so that would mean that we have identity minus p, putting this on the other side, times M equals the identity, or M being simply I minus p inverse. In order to calculate that, we should be careful, or we can remove unnecessary parts. You already know that if j is a recurrent state that is accessible from I, then Mij must be infinite. Once state j is visited, the chain will visit it again and again. So our expected number of being in that state is infinite. So that means that we are really only interested in the transient states. As for that, we have non-trivial solutions. So let T be the subset of transient states. If S is our state space, the set of all states, then we are interested in MTT. So the mean time spent in the transient states, given that the chain starts in the transient states. If it would start in a recurrent state, it would never visit any other transient states. So by that, we are really only interested in starting in a transient, staying in a transient state. Yeah. So MTT, this matrix we want to solve, and that can be by the system here be written as identity plus PTS MST. So this sum here that connects those matrices is still, of course, over the whole state space. Now, observing that actually, so we can split the state space here into the transient states and the complement of all transient states. So TC are all recurrent states, and this class in itself is closed, so one can never go back from TC to T. That means that the matrix M has a zero entry in that part, so where we start in a recurrent state and move to a transient state. Such transitions are impossible. Therefore, also the mean time spent in a transient state after starting in a recurrent state must be zero. With that part being zero, this matrix multiplication actually simplifies that the sum can only has only non-zero entries for the indices in the transient states. So we have actually a matrix multiplication PTT times MTT. Now we can solve in the same way as already indicated the system here now for MTT. So we have identity minus PTT inverse. As an example, look at this simple graph here. So we have here two transient classes. So starting in 2, we can leave this class, but not come back. So this is a transient class. This again is a transient class, ingoing, outgoing, but no way back. The transient class in itself. This is a recurrent class, and that is a recurrent class. You already saw this example in last week's lecture. And now we are interested in the behavior or the mean time spent in those two states, given that we either start in state 2 or in state 3. So our transition matrix is 0.2 and 0.3 and 0.5 for here. And we simply have to take 1 minus this and invert it. So 1 minus this matrix becomes this here. And then we have to invert it. It gives us this matrix. So we find that starting in state 2, the chain stays 1.25 times in state 2 and 0.75 times in state 3. While starting in state 3, of course, there's no way to go back to 2. So there's an expected time of 0 times to spend in times 2. And on average, 2 times spent in times in state 3. Now, if we want to find the transition probabilities, Fij, so starting in state I, ever going to state j, then they can be related to the mean times spent in these states by this following equation. So here is a proof for that. So we have to take Mij minus this identity matrix element and divide it by a diagonal element Mjj. So as a final topic, very briefly, sometimes it is important to have time reversible Markov chain. So we can look at a stationary, so to have a reversible Markov chain only makes sense if we have a stationary distribution, also a stationary Markov chain, because otherwise we cannot extend, of course, reading the chain in reverse time direction. The chain would suddenly end at 0. So in order to prevent that, we start with a stationary distribution. We have a stationary irreducible positive recurrent Markov chain. with the transition matrix and stationary distribution P. Then we can read this chain in reverse time order. And this is again a stationary Markov chain with a stationary distribution P and the transition matrix Q, say. And the Markov chain is called reversible, time reversible, if reading it for, in the one direction or the other direction, it's the same Markov chain. So it has the same transition matrix, so P equals Q. To have a criterion for that, the following theorem says that a Markov chain is time reversible if and only if the following so-called detailed balance equation holds. We have Pi times Pij, the transition matrix, equals Pj times Pji. So that must hold for all ij. And so this here, let Qi be the transition in reverse order. So going from state I to state J in reverse order. So that means, given that at a time minus n, the state is in I, that at the previous point in time, what's the probability that at the previous point in time it was in J? So because of stationarity, we can simply move the index to a positive one. So at some point m being in state I, what is the probability to one step before being in state J? That probability is Qij. And using Bayes' theorem, we can relate that to the reversed order, namely the probability that xm equals I, given that at the previous point in time it is in J, times the probability that xm equals J divided by the probability that at the previous point in time it was in I. That is a simple application of Bayes' theorem. And with that, this is Pj, this is Pi. This is the transition from J to I. And then we can simply multiply here by Pi, and we have Pi Qij equals Pji times Pj. Now, if P equals Q, then this Qij must be Pij, which exactly gives then this equation. So if you have an irreducible chain, then there exists some probability distribution. So if we have some probability distribution P such that this detailed balance holds, then Xn is time reversible, positive recurrent with the stationary distribution P. So this theorem actually solves a few questions, while here we assumed that actually we have a stationary chain, and then looked at the question of time reversibility only. We have here simply an irreducible Markov chain, and then look at the problem of detailed balance. If this detailed balance equation has a solution, P, then we have several results. Firstly, P is the stationary distribution. Our chain therefore must be positive recurrent and also is time reversible. So that is a strong result that in the case that the chain is time reversible, we can also answer the question of a stationary distribution. So that would be the proof. I don't want to spend any time in this lecture for this theoretical part, as it's anyway of minor interest, and that actually ends today's first lecture. Thank you for attention. Bye-bye.